Hi everyone. In this video, we are going to learn reasonings and fallacies. First, the reasoning part. We have two reasonings. One is called inductive, one is called deductive. So let's look at this one by one. First, we are going to look at inductive reasoning. Basically, inductive reasoning is that you do observations, individual observations. You study specific examples. You talk to other people, read newspaper. Basically, it's a process of gathering information in order to understand what's going on, and then you try to draw a general conclusion, conjecture, and this process is called inductive reasoning. For example, here, this is general structure. You do observations, you study specific examples, then you try to identify pattern and try to generalize your findings. And that process is called inductive reasoning. Here's a summarization of that process. It is a process that uses specific examples to draw a general conclusion. Now let's look at our first example. John received an A in every course he has taken at Gateway Technical College. Conclusion, he always received an A at Gateway. So basically, this general conclusion is based on the fact that so far he has received an A for every single course he has taken at Gateway. So the conclusion is that he always gets an A at Gateway. I don't know how you think about this kind of reasoning. Do you think he will get A for the rest of courses, every single course in the future also? Is there a guarantee for that? Probably not, right? Even though he has received an A for all of the courses he has taken so far, but that doesn't guarantee in the future he will receive an A for every courses in the future, right? So in other words, this from individual observation to draw general conclusion, inductive reasoning only tell you how likely what's going to happen in the future, but there's no guarantee it will happen in the future. In other words, inductive reasoning is not a valid reasoning process, and it won't give you a valid conclusion that he always receive A in the future at Gateway. There's no guarantee for that to happen. Now let's look at second inductive reasoning example. The first time I pulled a coin from the bag, it was a penny. The second coin I pulled was also a penny. The third time again was a penny. Therefore, that's the conclusion, right? Therefore, all the coins in the bag are pennies. Try to imagine if you were that person who puts a penny. See, first time I got a penny, second time I got a penny, third time I got a penny again. It must be all of the coins in the bag are pennies. Otherwise, how could I get pennies every time, right? So this is a general conclusion based on individual experiment or individual observation. Basically, again, you draw the general conclusion from individual experiments, individual observations. And this process is called inductive reasoning, from specific to general conclusion. If we think about that from common sense, just because you draw a penny in the first 3 times, there's no way guarantee you all of the coins in the bag are pennies. For example, if there are totally 100 coins in the bag and 99 of them are pennies, there's only one that is not a penny. Guess what? Next time you draw it, it's more than likely you still get a penny. But that doesn't mean all of coins in the bag are penny. It's just more likely to be a penny. There's no guarantee. Again, this kind of reasoning is not valid reasoning. It's a strong argument, but it's not a valid one because there's no guarantee your conclusion is right. Okay, now let's look at another one. The third one here. it says based on the following observations. So these are the observations. Say, for example, if you are looking at this these ratings, 1 plus 1 equals 2. That's right. 1 plus 3 equals 4. That's right. 3 plus 5 equals 8. They're all correct. And then you notice that, oh, these are two odd numbers. The result is even number. These two are odd numbers, result even number. The rest is a very similar situation. After these 6 observations, you may want to draw a conclusion that odd number plus odd number will be equal a even number. So now this is our conclusion. We can see that n. I wrote this myself. This is a typo. We can see that an odd number plus an odd number equals a even number. So that's the conclusion. In this case, it is correct, but that doesn't mean this reasoning method is a valid one. Okay. So the reason I use this example is that I want you to see this process. When you use individual observation to draw general conclusion, odd number plus odd number equal even number, this process is called inductive reasoning. Okay, now the last example. So let me just display part of this. So this is the question itself. Guess what comes next? So if we look at it, we notice the shape first. Square, triangle, square, triangle, square, triangle. Say after these 3 pairs, you would say the next must be a square, right? So you base your conclusion on specific examples. You notice that after square, you got a triangle. After triangle, you got a square. After square, you got a triangle. They just alternate, right? This is called a pattern. Whenever you identify a pattern from your observation, that process is called inductive reasoning. Inductive reasoning. And once we get a pattern, then we use that pattern to predict what's the next. It's also part of inductive reasoning. So we know the next one going to be a square, but we have 2 different kinds of squares. One is totally black stick square. The other one has a white dot in the middle. So which one should be this one? Now we look at the square pattern. The black square, white dot square. Black square, white dot square, right? We should have a white dot square in this place, and this is the answer. So this whole process is still called inductive reasoning because you form a pattern by looking at the examples. Based on your observation, you form a pattern. Forming a pattern that process is inductive reasoning. When you use a pattern to predict the next one, it's also part of it. Now that's inductive reasoning. Now let's look at deductive reasoning. Deductive reasoning is a process that we draw a specific conclusion from a general statement. It is a basic form of valid reasoning. What that means is that for deductive reasoning, first you have some facts, or you have some established theory, or you have some general statement, something that is already proven. You have that in general. Then you want to draw a conclusion on a specific case, and that process is called deductive reasoning, from general to specific. And the deductive reasoning is a basic form of valid reasoning. In other words, if you use the deductive reasoning, usually your argument is a valid argument. Your conclusion is going to be right. Now let's look at example 1. All computer chips need electricity to work. So that's a general statement because this refers to all of computer chips, not specific ones, all of them, general. Now we go to specific. A CPU is a computer chip. So everybody knows that. This is a specific one. We're talking about CPU, not general computer chips. Specific one. It's a computer chip. So a CPU needs electricity to work. We know that's true. We know that's true is because this argument, this reasoning process is called deductive reasoning. It is a valid reasoning process. All computer chips need electricity to work. This one is computer chip, so it will need electricity to work from general to specific. And actually, we can prove this reasoning is valid by using the technique we learned um, in the last lecture, basically in an Euler diagram. I don't know if you still remember that or not. All computer chips need electricity, like O, A, or B. These computer chips, all of them, need electricity. These are all of those things that need electricity. This is larger circle. Now a computer, a CPU is computer chip. That means CPU has to be put inside computer chip circle because it is one of those. Now let's look at the relation between a CPU and electricity. Apparently the CPU also in the circuit for those that need electricity. So CPU need electricity. That's just a valid argument. But you don't have to use all of them in this section because we learned this deductive reasoning in itself is a valid reasoning process. Now let's look at another example of deductive reasoning. Example 2, an even number plus an even number will be another even number. See, this is a general statement because they didn't mention specific even numbers. There's an even number, basically. This is an even number, any even number. An even number plus another even number will be another even number. Now, if you look at this addition, in 4 plus 6 equals 10, we add two even numbers, right? Even if we don't know the result is 10, we can draw the conclusion that the result will be another even number because this is the even number plus even number. This is a specific case based on the general statement, and we can draw the conclusion on the specific case. So 10 is an even number. So this is the deductive reasoning process. This is some kind of a discussion between inductive reasoning and deductive reasoning and their validity if you use that to make an argument. And inductive reasoning can make a very strong argument, just like the one that the first 3 times you put a penny each time, right? Then you draw your conclusion that all of the coins in the bag are pennies. So that's why it says you can make a strong argument. See, each time I get a penny, they must be all pennies, right? So you can make a strong argument, but we can never prove that inductive reasoning is a valid argument. Why is that? Because in order to prove it is true, you have to prove every single case is true, and that's impossible. For example, imagine if you have a huge bag, the bag in theory contains 1 trillion coins. Can you prove every single one of them is penny by putting them one by one? That's not possible. So the inductive reasoning in itself is very hard to prove. You have a valid conclusion. So generally, we don't use inductive reasoning to make a valid argument because we can't. And on the other hand, deductive reasoning is a basic form of valid arguments. In other words, as long as your premises are correct, you use deductive reasoning, then your argument is going to be a valid one. Okay, now we switch to another topic, different topic. It's the fallacies of inverse and converse. First, let's lay some background before we can talk about inverse and converse. First, conditional statement. So what is a conditional statement? If we use if-then structure to form a statement, that statement is called a conditional statement. Example, if I go shopping, then I will buy some vegetables. You don't have to write that word then you just connecting word, right? To introduce the consequence. I go shopping is a condition. I will buy some vegetable is a consequence. So if I go shopping, then I will buy some vegetables. Now this is called a conditional statement. We can symbolize these two sentences. So this is the one sentence here. This is the one sentence. So we want to symbolize this in order to talk about words later on in a more efficient way. So when you symbolize this, basically use one letter to represent each statement. We use P to represent I go shopping. In theory, you can use any letter to represent these sentences, but traditionally, in logic, this is subject, we use P, Q, R. Other than that, there's no restriction which letters you can use. So let's use P to represent this sentence, I go shopping. Then we use Q to represent I will buy some vegetables. Then this original conditional statement, if I go shopping, I will buy some vegetables, can be written as this. And this arrow means if then. And if is this part, this is the consequence, this is that. If this happen, this will happen. If I go shopping, then I will buy some vegetables. So this is symbolized so that we don't have to write these two sentences each time we talk about this conditional statement. Now, let's look at what is the equivalent statement of a conditional statement. In other words, if you have a conditional statement, is there a way to say something that is equivalent to your conditional statement? So let's look at it. Now, this is an example with different sentences, but we want to explain the meaning of equivalent statement of a given conditional statement. Okay, this time I want to use P to represent this one, this sentence statement. I am a father, that's P. Q is supposed to be lowercase. As a Microsoft Word, we will capitalize the first one automatically. So we use a Q to represent I am a man. So that means if we go if P then Q, it really means if I am a father, because P is a father, right? If I am a father, then I am a man. If I am a father, then I'm a man. Is that correct? Is that true in real life? That's true, right? If I am a father, then automatically I'm a man. I am a man. So this is true. Now we want to say the equivalent of this statement. Now here's the equivalent. If I am not a man, then I am not a father. Now we need to pause here for a moment. Think about that. What is called equivalent? Equivalent actually means this. If the original statement is true, this one has to be true. That's called equivalent. They're equivalent in terms of truth. Okay. The first one, original one was, if I am a father, then I am a man. You know that's true. Now, how about this one? If I am not a man, then I am not a father. This is also true. This is also true. Traditionally, at least we don't talk about those adoption, gay, those. So traditionally, if you are not a man, you cannot be a father. That's for sure. So this is also true, the equivalent. But if we look at a symbol to see what happens, originally it was if I'm a man, I am a father. Originally, we have this structure. And this one is that if I am not a man, I am man is represented by Q. If I am not a man, then I am not a father. That means this I am man become a condition. You just negate that. So we put a Q as condition now. I am a man. This small title in front of this represents negation. So originally, if I only look at Q, it really means I am a man. If you put this symbol in the front, it becomes I am a man. And this is the condition. So if I am not a man, then I am not a father. That's this. Basically, that's a new sentence. And this is equivalent to that. That's a key thing to form an equivalent statement of a conditional statement. So let's see how this structure works. This is original. Doesn't matter the specific meaning of P and Q if you only look at the structure. In order to form an equivalent statement, you need to do two things. First, switch between these two. Consequence become condition. Condition become consequence. Not only that, you have to negate each after you switch. Then you get something that is equivalent. Let me give you an actual example before we look at the next one. A dragonfly. If I just try to think of example on the fly. If it is a dragonfly, it has wings. That's true? That's true, right? Now, how do we form an equivalent? Remember, we switch between the condition and consequence. This condition, this consequence. We switch them and we negate them. If it doesn't have wings, right? We switch it, become condition and negate it. Have wings. Then this one become consequence, it also negated. It is not a dragonfly. Is that still true? It's still true. If it doesn't have wings, sure, it's not a dragonfly because dragonfly they all have wings. So they are equivalent. If the first one true, this one will be true. Equivalent means they have same truth value. They're both true. Now let's look at just another example here. Let's use P to represent you are a human. Q represent you use lungs to breathe. So now if P then Q really means if you are a human, then you use lungs to breathe. So this is true. We know this is true. Now the equivalent is this structure, right? Remember, switch and negate. This will be equivalent. You don't have to write the symbols when you make equivalent statement. I use the symbols to simplify things so that you can see the structure. Now we switch this to become condition and negate it. If you don't use lungs to breathe, then negate this. You are not a human. Is that still true? If you don't use lungs to breathe, then you are not a human. Yeah, that is still true. Okay. This is just a conclusion that this is called the contrapositive statement of this original. This conditional statement, this is the equivalent statement. This equivalent statement we call it contrapositive. In other words, when you switch between condition and the consequence and negate them, you get a contrapositive statement, which is equivalent to this, to the original. Okay, now we are ready to talk about those fallacies. One is called a converse statement. One is called inverse statement. No matter you have converse or inverse statement, they both are fallacies. Now let's take a closer look. Now, if we have a conditional statement, if P then Q, then the converse statement will have this structure. This is structure. That means how do we form a converse statement? We simply switch these two. The consequence becomes the condition become consequence. The result is called a converse statement of original one. Example, let's look at this original, okay? P represent I am a father, Q represent I am a man. So this conditional statement is P, if P then Q, which means if I am a father, because P I am a father, if I am a father, then I am a man. You know that's true. You know that's true. Now let's look at the converse. The converse is nothing more than switch between these two. See, Q, if Q turn P. Q means I'm a man, right? If I am a man, then I am a father. Think about that. Is that necessarily true? Is that necessarily true? If I am a man, then I am automatically a father? You know, the common sense is not necessarily true. A man is any male adult, but to be a father, you have to have a child, right? There's many millions of people, millions of male who don't have children. Sure, they are men, but they are not father. So this is false. This is false. You see, originally is true. Original conditional statement is true. But when you switch between condition and consequence, the resulted statement is not necessarily true. That's why converse statement is a fallacy. It's not true, not necessarily true. Don't rely on that. In the real life, sometimes you make statement, it sounds like true. That's why it's confuse people. But in general, logically speaking, from here you can see it's not right logical reasoning. It's false. Now let's look at another one, different types of converse. Determine if the conclusion is true or false. Start from here. If a person is a professional swimmer, then he or she can swim fast. That means a professional swimmer will swim fast, no matter he or she, right? Now, Jason can swim fast. Can we draw the conclusion that Jason is a professional swimmer necessarily in real life? If a person is a professional swimmer, then that person can swim fast. We know that that's true. Otherwise, you cannot be a professional if you swim very slow. How come you attend any contact or contest, right? And race, you're not going to win if you're slow. So a professional swimmer will be fast. But just because Jason can fast, does it necessarily mean he is a professional swimmer? You know, that's not true. Many people can swim fast too, but they never enter into this profession as a swimmer. So this conclusion is wrong. So what's wrong? If you understand, that's why we learn this structure. If you realize this actually is a converse statement, you know automatically the conclusion will be wrong. Look at that. If you are a professional swimmer, then you swim fast. So let's use a P to represent professional swimmer. This is P. And this swim fast is Q. So basically, this whole thing is if P then Q. Now this one, Jason can swim fast. Swim fast, this Q become a condition. Then does it mean Jason is professional swimmer? No, this is the converse. This logic is wrong. So if you realize this logic structure, you don't even need to read this specific sentence to determine if this is true or not, because this switched between condition and consequence. Now, this just tell you, now Jason swim fast, then Jason is a professional swimmer. It's pretty much like if you swim fast, then you're professional swimmer. They just switch between condition and consequence. That's converse, and it is false logic. We see that from the previous father and the man example, right? This is also true from real life. Just because one person swims fast doesn't mean that person is a professional swimmer. We know that kind of logic is. Okay, conclusion, converse statement is fallacy. Now let's look at inverse. And given the conditional statement, if P then Q, then the inverse statement will have a structure which is this. So compared to the original and the inverse, what happened? What happened is that this time we don't switch them, okay? We just negate both sides without switching. P is still a condition, Q is still conclusion. We just negate them in the front. Now let's use this further main example to illustrate how ridiculous this inverse statement, inverse fallacy, if people believe this is true. Now P again, I am a father. Q, I am a man. So if P then Q means if I am a father, then I am a man. So everything is just like previous one. Now this is inverse. We're going to negate the condition. We're going to negate the consequence to see what happens. Now the meaning of this, if I am not a man, before this P is I am man. If I am not a father, the P is I am a father. Negated, I am not a father, right? If I am not a father, then I am not a man. Is that true in the real life? Just because you're not a father, then you're not a man? That's wrong. We know that's wrong. Because again, a lot of people a man, but they just don't have children. You cannot say an adult male is not a man just because that person is not a father, doesn't have children. That's wrong. So we know this inverse statement is wrong. Inverse. So let's look at another example. Determine if the conclusion is true or false. This is kind of similar to your homework problem, I guess. Now let's look at this one. All mathematicians are smart. Then what does this mean? It means if you are a mathematician, then you are smart. It's equivalent to a conditional statement. Now it says Jason is not a mathematician. This is the separation between the pieces and the conclusion, right? So based on this tool, can we draw the conclusion that Jason is not smart? So again, let's reread this. If you are a mathematician, then you're smart. That is equivalent way to say all mathematicians are smart. Now, Jason is not a mathematician. Can we draw the conclusion that Jason is not smart? Absolutely not. Because we know in real life, you don't even need to learn this in this course, that besides mathematicians, there are many other smart people for sure. So this conclusion is wrong. But we want to determine this conclusion is wrong, not based on our common sense or personal experience. We want to base it on the logic, based on the structure. So what happens is here, all mathematicians are smart. It really means if you are a mathematician, then you are smart. This is the first one, equivalent. That means if I use P to represent this, if you are a mathematician, I use Q to represent you are smart. Then the original is if P then Q, right? Now what happens here is that Jason is not a mathematician. This is a mathematician, right? So it becomes this. If Jason is not a mathematician, can we draw the conclusion that Jason is smart? This is smart, right? Not smart. This is inverse, exactly inverse structure. You know inverse structure is a wrong logic. That's why this one is wrong, this conclusion. In other words, if you identify this kind of structure, you don't even need to read this to know this is wrong. No matter it's about a mathematician or not, this logic is wrong. I hope I help you understand better about inverse fallacies and converse fallacies. Inverse statement is a fallacy. It's not reliable conclusion. Okay, you guys, in the next video,